Okay, what we started with in our class, and I don't know if these numbers are exactly right, but they're kind of close. We started with 290 wrapped peppermint candies in a bag, but the students were not told how many candies were in the bag. That's important. So all this part you don't read. This is in the back of your mind and you pretend you don't know it. Student volunteers chose and marked 25 candies and put the candies back into the bag. Another group of volunteers chose 32 candies from the bag and found 7 marked candies. Based on what the students knew, how many candies should they have predicted were in the bag? So for example, if you say 290, that's definitely wrong. Okay? So you don't know, pretend like you don't know how many. Okay, so as far as they were concerned, they started with X candies. Okay? And then they said 25 of the X are marked. Okay? And then another selection was taken, and then they found out that 7 out of 32 are marked. So what we're assuming is it's the same ratio. So you say 7 over 32, and you say that's about 21.875%. So the selection they picked was 21.875. So if the 21% were marked, but 25 were marked, then you do the following. You say 25 out of X equals 0.21875, and you solve for X. So you multiply both sides by X, and then you solve for X. Okay, then you divide both sides, so you say 25 divided by 0.21875 equals, so you should be saying 114.3, and the reason I want you to put the 0.3 is I want you to be aware that it's not an integer. Okay, so estimate about 115 candies, because we know that no manufacturer is going to put 114 in the container, and the students actually knew that I opened a fresh container, so they could guess there's 115. Were the candies well mixed between the two samplings? No. So if they'd been well mixed, how many should there have been? If they'd been well mixed, okay, then, so we knew it was 21%, so it would be 290 times 0.21875 is equal to what? 290 times 0.21875 tells you how many should have been. So about 63 or so should have been marked. 63 or so should have been marked. Okay, so this is not a statistics class, but some things are so obvious that you don't need to actually study statistics to tell that we're really, really far off. You need statistics to tell you when you get close how likely something is to happen. But when something is so badly off like this, you can just go ahead and say that without even pulling out the fancy tools. You can say 7 were marked out of, I'm sorry, not 7, 25 were marked, in other words. 25 of the whole were marked. But if 21% had been marked, then 63 would have been marked. And we only had 25, and says 25 and 63 are really far off. 63 is way larger than 25. So what's another way you could analyze this, of analyzing how many should have been marked? You could have said this. You could have said, well, if we knew that 25 out of the whole were marked, we could say, well, what is that ratio? You could have said 25 out of 290 is what ratio? So then you could say 25 divided by 290 is 0.086, so 8.6%. So is equal to 8.6%. And then you could have said, well, what is 8.6% of the 32 we collected? So 32 times 0.086 would have been about 2 or 3 candies, about 3 candies. Or so you could have said 0.086 times 32 is 2.7, should have been marked. Okay, I'm writing it in a different color because I want to indicate that this whole argument is one entire argument, or this entire argument is a whole separate argument. You wouldn't do both arguments. You just say one or the other. I'm just saying that you don't have just one option for a correct answer. There's a lot of ways to approach this, and they're all correct. The point is those two ratios, we're making the assumption that this ratio and this ratio are the same, and they are indeed not the same, which indicates that the mixing did not occur. So again, you can attack that from either angle to show that those are not the same.